So, hello students. So, due to power cut, I had to stop the video yesterday. So, let us continue from that thing, from the thing that where we stopped. So, we are reading about capacitance. We are studying, we are learning capacitance. But before that, we understood the concept of that difference between conductors and insulators. Okay, we understood free charges, we understood bound charges, or the charges which are bound to their nucleus. Even after giving some energy, you are not able to free that electron or the outermost electron from their nucleus. Okay, so one more difference, and we shall be studying the behavior of a conductor inside of an electric field. So before that, for a conductor, and it is for an insulator. Okay, for a conductor, the valence band and the conduction band are, it is valence band, it is conduction band. They are overlapped. Okay, there is no such separation. They are overlapped. The conduction band and the valence band, they overlap each other. Okay, that's why so many free electrons are available. But in case of insulators, it is only a graph. Okay, it is only a energy. It is only an energy graph. You will be reading about this in the next classes if you join physics or material science. So it is an insulator. It is the graph of a conductor. It is the graph of an insulator. If it is the valence band, it is the conduction band. You can see that actually there is a large energy difference. There is a large energy difference between valence band and conduction band. And to just conduct electricity, electrons have to jump from this band to this band. They have to jump from valence band to conduction band in order to conduct electricity. So this gap is quite large. This is called energy gap or energy band gap or anything you can say, but it is a gap. It is something that electron should, in this valence bond, should be able to jump conduction band only if it gets the energy equal to energy gap. Okay, energy gap का जो एनर्जी डिफरेंस है, अगर इलेक्ट्रॉन वैलेंस बॉन्ड पे है तो वो एनर्जी गैप का जो एनर्जी अगर उसे मिल जाता है, देन इट कैन जंप इनटू कंडक्शन बैंड. सो ये वैलेंस बैंड से कंडक्शन बैंड को जंप कर सकता है एंड इट कैन कंडक्ट इलेक्ट्रिसिटी. सो ये था कंडक्टर का, ये था इंसुलेटर का. ये एक डिफरेंस है, आप लिख सकते हैं. सो अगर हम इंसुलेटर को एनर्जी प्रोवाइड करें, इफ वी प्रोवाइड एनर्जी टू insulator, the energy that is equal to that energy gap, in that case it may happen that electrons from valence bond jump to conduction band and then start conducting electricity. So this can happen if we increase the temperature of that insulator. This can only happen if we increase the temperature of that insulator. Temperature, if we are increasing temperature, that means we are heating it. Heating it means we are giving it any energy. Okay, so when temperature is applied, insulator can conduct electricity. Okay, when temperature is increased of that insulator, it can conduct electricity. Okay, and conductor can conduct electricity as well. So it is one difference you can write. So you can write in conductors, conduction band. Okay, conduction band and valence band are overlapping each other. They overlap each other. एक ऊपर के ऊपर मिले हुए हैं, overlapping each other. Okay, that's why so many electrons can go from valence band to conduction band, since they are overlapping each other. And in this case, there is an energy gap. There is a large energy gap. There is a large energy gap between CB and VB, between CB and VB. There is a large energy gap between CB and VB. So, can you actually tell what should be the length of this energy gap? So, it is of the order of the electron volts. The previous energy unit we have learned in the previous classes of electric potential energy. This thing is of the order of some electron volts. Larger is this gap. That means electron requires larger electron volts in order to jump from valence bond to conduction band and then become free. Okay, these are the things you can write. You can differentiate in between. So now let us start. The behavior of a conductor inside of an electric field. So today we shall be learning about the behavior of a conductor inside an electric field. So in order to produce an electric field, you just produce two parallel plates. This is a parallel plate, and you charge one of the plate positively. This is positively charged. आप एक को positively charged कर सकते हैं, and the other negatively charged. और दूसरे को negatively charged कर सकते हैं. अगर आपको याद होगा, if you remember, then electric field lines. Can you draw electric field lines in this setup? Yes, you can actually draw. आप ये draw कर सकते हैं. कैसे draw करेंगे? Electric field lines start from the positive side of the parallel plate to negative side. Okay, this is the electric field line, and it should be straight lines and equidistanced. Okay, this is the drawing of electric field lines. ऐसे आपको draw करना है. Now you have to place a conductor inside that field. You now have to place that conductor inside of that field. So that conductor may be of any arbitrary shape. Okay, the conductor may be of any arbitrary shape. So for our drawing to look beautiful or to look good, draw another set of parallel plates and place a rectangular conductor inside of it. Just place a rectangular conductor inside of it. Yes, it is visible. So when it is placed inside an electric field, you can actually see charge separation. Inside the conductor. So we have placed a conductor inside of an electric field. So for a conductor, when it is placed inside of an electric field, तो क्या होता है? Charges separation occurs. Okay, charge separation occurs. The side closer to the positive plate will acquire negative charges. Okay, will acquire negative charges. जो साइड पॉजिटिव प्लेट के पास होगा उस पर नेगेटिव चार्ज आ जाएगी, और जो साइड नेगेटिव प्लेट के पास होगा उस पर पॉजिटिव चार्ज आ जाएगी. ओके, एंड द साइड दैट इज क्लोजर टू द नेगेटिव प्लेट विल एक्वायर पॉजिटिव charge. Okay, such is the charge separation. You can actually see such is the charge separation. Now you can also see that whenever a charge separation is occurring inside of a conductor, the right side is getting positively charged and the left side is getting negatively charged. That means an electric field is set up inside of a conductor. The electric field is set up inside of the conductor. Now let us draw electric field lines. What is the electric field lines? It is the same concept. You just draw electric field lines from the positive charges to the negative charges. This is the concept of electric field lines. It will start from the positive charge and will end at the negative charge. Okay. So you can see that it is E external. This is external field, and it is E internal. It is internal field. Okay, so even if we increase the external field we will see that the charge separation becomes more intense. The charge separation becomes more intense, and more charge start to come over to the surfaces of that conductor, forming an electric field that will exactly be equal and opposite to the external electric field. So क्या होता है, अगर हम इलेक्ट्रिक फील्ड एक्सटर्नल इलेक्ट्रिक फील्ड को बढ़ाते भी हैं तो उसका इफेक्ट क्या होता है कि चार्ज सेपरेशन ज्यादा से ज्यादा होता है, ज्यादा से ज्यादा चार्ज सरफेस और साइड को आते हैं. दैट मीन्स इलेक्ट्रिक फील्ड इनसाइड इनसाइड का जो इलेक्ट्रिक फील्ड है वो भी स्ट्रॉन्गर और स्ट्रॉन्गर बनता रहता है. एंड ये उतनी देर तक होता है जितनी देर तक इनसाइड इलेक्ट्रिक फील्ड और एक्सटर्नल इलेक्ट्रिक फील्ड इक्वल नहीं हो जाते. दैट मीन्स E inside equal to E external for a conductor. Okay, for a conductor. That means there is no, so E net, what is E net? The net electric field is E external minus E internal, that will give you 0. So there is no electric field inside of a conductor. There is no electric field inside of a conductor. So this is positive charge, this is a positively charged plate, this is a negatively charged plate. So you can actually draw electric field lines that do not pass through the conductor. Electric field lines won't pass through this conductor. So if you want to write statements, just follow my words, that to check if a conductor, to check the behavior of a conductor kept inside of an electric field, what do you need to do? You need to have a setup of a parallel plate in which one plate is positively charged and the other plate is negatively charged. You place a conductor of any arbitrary shape inside of that electric field and you will see that charge separation is happening. The side that is closer to the positively charged plate will acquire negative charges and the side that is closer to the negatively charged plate will acquire positive charges. And for that, there should be an electric field set up inside that conductor. And that electric field for a conductor is equal to external electric field, for which the net electric field becomes 0 inside that conductor. So you can actually see that there is no electric field inside of a conductor. So electric field is 0 inside of a conductor, which we have learned in the previous chapters of electric field. Okay, so this was the behavior or electric field. You can write the statement as electric field is 0 inside of a conductor. You can actually write it, of a conductor, or in other sense you can actually write there is no electric field exists inside of a conductor. Okay, no electric field exists inside of a conductor. This was our first point. Now let us come to the second point. What is the second point? Okay, what is the second point? So before starting that, we have to remember the relation of electric field and potential gradient. I hope that you know the relation between electric field and potential gradient is E is equal to minus dV upon dx. That means electric field is equal to the negative gradient of potential. Okay. So before starting that point, I need to give you another concept of electrostatic shielding. So it is related to this concept, electrostatic shielding. Electrostatic shielding. We shield something from something by the help of electrostatics. Now consider the situation. Then you are in the open ground, this is an open ground, and you are facing severe thunderstorm. Okay, and numerous thunderous lightning strikes. Okay, it's quite so often. So you have a house that is a temporary tent. Okay, it is a tent, bridge. You can go below the bridge. This is a bridge. This is a tree, and there is a metal container. There is a metal container. So you are here, and numerous thunderous lightning strikes is going. Many lightning strikes. Okay. Now, out of fear and to save yourself, you have to choose any one of these four places to hide. So, which is the safest place? To ensure our survival, we have to go to the safest place. Okay, we can hide under anything, but which is the safest place? We don't know. So, the safest place to go inside, can you guess? Is it a tent? Is it a bridge? Is it a tree? Or is it a metal container? So, the safest place is a metal container. You should go inside of the metal container. It should be a metal container that will cover you from every side. Why is it so? Why is tent not the safest place? Why is not the breeze is the safest place? Why is not a tree going under a tree is not a safest place? Why metal container is a safest place? Why? Because since a metal container is a conductor, since a metal container is a conductor, the net electric field inside of a conductor is zero. That means if you go inside that metal conductor, these electric or lightning strikes won't affect you inside of that metal conductor, since it will cancel the external electric field. So this is the safest place for you to go inside of that metal conductor container, so you can save yourself. This metal container may be a car or maybe a truck. You can actually hide inside of those things. Okay. So now you can actually see if this is not the actual concept of hiding inside. But what is the application of electrostatic shielding? What is the application of electrostatic shielding? If you put an electron inside of a metal conductor, if you put an electron inside of a hollow metal conductor, since electric field is zero inside of that metal conductor, it won't be affected by any exterior field. It won't be affected by any exterior field. Now, if the electron is to work for anything, then it can work inside of that conductor. If any electric devices is given that works on the electronic charges, then that electronic device, if it is covered by or it is contained inside of a metal container, then the external field won't be affecting the electron or the charge inside of that electronic device, which will work in a proper condition. But in case it happens that for some electronic devices or any sensitive devices where measurement is very necessary, the external field somehow can interfere with the inside of the sensitive instrument. So to avoid this, what we do, we cover the sensitive instrument by a metal box, so that it acts as a seal. It acts as a seal from the external electric field. That is the concept of electrostatic shielding. Okay. So now let us come to another concept. No charge reside inside of a conductor. No charge resides inside the conductor. Inside a conductor. Why is it so? No charge reside inside of a conductor. Now, if you consider a metallic conductor, there is a cavity inside of it and there is a charge inside of it, that is Q. Okay, if it is possible for you to assume that inside of a metal conductor you have considered a cavity that contains a charge Q. Okay. So, if it consists of a charge Q, then we can actually calculate the electric field inside of that conductor. That means by the application of Gauss's law, we consider a Gaussian surface. that consists of that charge q. Okay. Now by the concept of Gauss's law, E dot S or E dot ds is equal to q by epsilon naught. Okay, the charge contained inside of the Gaussian surface is q. That means E has a non-zero value. But in the previous concept, we learned that electric field inside of it is actually zero. It is a proven concept. That means to find electric field inside of it zero, there must be a quantity that is equal to this thing and opposite to this thing. That means that negative of q by epsilon naught is minus q by epsilon naught, that will cancel the electric field inside. That means it is not possible that a charge is inside of a conductor. So there must be another charge that is opposite in magnitude of the considered charge that will make the electric field to be the net electric field to be zero inside of the conductor. Okay. So the charge given to a conductor always reside on the surface. The charge given to a conductor always reside on the surface. So there is no charge inside of a conductor. So now we shall be learning about another concept. No charge resides inside of a conductor. All the charge given to the conductor reside on the surface. All the charge reside on the surface. On the surface. Okay. So now let us do another thing. Electric field lines are always perpendicular to the surface of that conductor. If it is a conductor, electric field line at this point is perpendicular to it. It is always perpendicular to it. But since electric field is inside zero, then how is it electric field coming? We are charging that conductor so that the charges are residing on its surface. Okay. And since there is charge, so we will get an electric field. So it is always perpendicular to the conductor, the surface of the conductor. And why is it so? Now, for this instance, you think that electric field is like this. Your electric field is like this. It is making an angle theta with the surface of that conductor. That means it has two components. One is this perpendicular component and the other is this vertical component. Okay. If it is E, then E sin theta is the perpendicular component and E cos theta is the parallel component. Okay. If there is a component along this surface, if there is a component along this surface, then charges reside on the surface. That means this electric field, the component of this electric field will try to move those charges. Will try to move those charges. Since we are considering static electricity, that means charges to be at rest. So we have to ignore this component. We have to assume that this component doesn't exist, because charges do not move in static electricity. That's why we prove that indirectly that electric field is always perpendicular to the surface. I hope that you have understood this concept. Electric field line is always perpendicular to the surface of the conductor. Electric field line is always perpendicular to the surface of conductor, Okay. Electric field line is always perpendicular to the surface of the conductor. Now the fifth point is potential inside of a conductor and on its surface is constant. Okay, the potential inside of a conductor and on its surface is constant. So how are you going to prove it? So let us consider any conductor. We know that electric field inside of it is 0. It is 0. And we know that E is equal to minus dV upon dx. Electric field is the negative gradient of potential. Now, if E is 0, that means dV by dx is 0. Which means V is a constant, which implies that V is a constant quantity. V is a constant quantity. Okay, V is a constant quantity. So electric field inside of a conductor is constant. Now we have added one more thing, that why is it constant on the surface? Why is it constant on the surface? Now in the same way, we learned that electric field is always perpendicular to the surface of the conductor. Now if there is charge, reside on the surface, then the parallel component should move that charge. If a charge moves, that means there should be a potential difference. If a charge moves from this position to this position, that means there is a potential difference. Since the parallel component of electric field is 0, there is no component of electric field along this line. That means charge do not move. Even so, if they don't move, that means the potential difference between those points is 0. If the potential difference between those points is 0, that means it is the potential at this point, let it be VA, and the potential at this point, let it be VB, then VA is equal to VB. Okay, if the potential difference is 0, then all of the surface is at the same potential. Okay, so I hope you have understood this statement. So let us write that statement. So what is that statement? Electric potential is constant inside and on the surface of a conductor. If you are given a conductor, then electric potential in its inside is constant as well as on the surface of that conductor, which we have proved now. So now we shall be learning the last point, that what is the electric field just outside the conductor. For this we have to consider a conductor. Charge is residing on it. That may be positive or negative. So for this case, let us consider that it is positive in nature. Charge reside upon it. This is our charge. So let us consider a Gaussian surface that is bigger than that conductor. Now if we apply the Gauss law, that is E dot ds will give you Q by epsilon naught. This is the total charge. The total charge content inside or on the surface of the conductor is Q. So this is the electric field. Now we don't know what is the actual value. This is ds, this is the area. We don't know the actual value, but it is equal to something s. And since you can see that it is always perpendicular to the surface and ds is also perpendicular to the surface, so the angle between E and ds is 0. If it is E vector, it is ds vector, then angle between EDS is 0. Consider EDS cos 0, Q upon epsilon naught. Now cos 0 value is 1. This is 1. Take E outside, and the closed surface integral is equal to the surface of the conductor is equal to Q upon epsilon naught. Now E is equal to Q upon epsilon naught S. This is your value of electric field. And now if you know that sigma, the surface charge density, is given as Q upon S, the total charge divided by the total surface area. Now you can actually replace Q by S by sigma. So E is equal to sigma by epsilon naught. This is your answer. So we have calculated the electric field value just outside of that conductor it is equal to sigma by epsilon naught. So this is our answer. We have found out the behavior of a conductor inside of an electric field. These are all the possible outcomes that could come. So the heading of today's topic is behavior of a conductor inside an electric field. Okay, these classes are not going to be short. These are in detailed classes. We are going to learn things in details. So they are somehow a bit long. If you want to learn the concepts by heart, you are welcome to watch these videos. Okay, these are the possible things that can come out of behavior of a conductor inside an electric field. We haven't even started capacitance now, but all of these things come under capacitance. How to understand capacitance? These are the basic things. Okay, so for today we are stopping this class right now. If you have any doubts, you can actually put a comment in the comment section, and I have given my contact details in the description box. You can actually contact me there if there is a problem regarding numericals, you are not understanding any numerical regarding these chapters. You can actually mail me. I'll give you a good solutions. And like our videos, support us, share the videos among your friends who want to learn electrostatics by heart in details. That will help you to the rest throughout the rest of your life. So up until then, take care, practice more and more, and we shall meet in the next lecture regarding capacitance. So thank you all.